Rotating crystal method. This is the one of X-ray diffraction method for the analysis of crystal structure. Using this method, we can find the lattice constant. Can find lattice constants like A, B, and C of the unit cell. The requirement for this method is requirements are we need cylindrical camera, monochromatic X-rays, X-rays having single wavelength, angle is variable, which is the glancing angle. In this case, the crystal is rotated and so glancing angle changes. And the last, single crystal. We need a single crystal. Then let me show this cylindrical camera. I am drawing here the diagram of the cylindrical camera. This is nothing but the light tight cylinder. This is the cylinder. And along the inner circumference of this cylinder, X-ray film is attached. Let me write that. On the inner X-ray film attached. So inside this cylinder there is a X-ray film along this. I am showing the dotted line for the X-ray film. That is the X-ray film. Then there is a rotating spindle on top of which crystal is mounted. Here is rotating spindle. This is spindle which is rotated. And this is rotated in this direction, and on which the crystal is mounted. Single crystal is mounted on top of this. This is the single crystal, and the single crystal is mounted on top of this rotating spindle. Let me write that. Crystal is mounted on rotating spindle such that its one of the axis is parallel to rotation axis. Let's say in this case, C axis is parallel to rotation axis. In this case, rotation axis is this. This is rotation axis which is rotating along this direction. So this is rotation axis, and parallel to this rotation axis, one of the crystal axis is parallel. So this is the crystal axis which is parallel to the rotation axis, and that axis in our case is C axis. So this C axis is parallel to the rotation axis. Then what we need is monochromatic X-rays. Monochromatic X-rays fall on this crystal, and then accordingly it is diffracted. So as you can see, this is monochromatic X-ray. X-ray, which is collimated into fine pencil beam. That fine pencil beam fall on a crystal. Let me note down that. A fine pencil beam of monochromatic X-rays falls on the crystal. As you can see here, that monochromatic X-rays which is collimated into fine pencil beam falls on the crystal. Now, We are using the single crystal here, and so interplanar spacing d is constant. What are the constant terms here? Constant terms are wavelength and interplanar spacing, and angle is variable. This theta is variable. So when Bragg's law is satisfied with this angle, let me write like this. If this theta satisfies Bragg's law, we get X-ray diffraction. Now look at this diagram. This is the single crystal, and this single crystal is rotated using the spindle. Now we will see the planes. Those are parallel to C-axis. We are considering planes. Consider planes which are parallel to C-axis. Now all those planes who are having Miller indices, which are these planes? These planes are having Miller indices equals to HK0. So L index is 0. L index 0 means that plane is parallel to C-axis. So let me show you here diagram. This is the incident X-ray, and these are the parallel planes to the C-axis. They are also parallel to rotation axis because C and the rotation axis are parallel. Now when this X-ray incident on this plane and this plane is rotating, so the angle is continuously changing. So at certain angle, Bragg's law is satisfied and you will get the diffraction. You will get the diffraction in the same plane. And as these planes are rotating, whenever that theta satisfies Bragg's law, you get diffraction of X-ray beam in different direction. But all these are in the horizontal plane. The plane is same, and that plane is this plane. Let me redraw again. This is the horizontal plane. And in this horizontal plane, you will get the all diffraction because this plane is perpendicular to the X-ray beam. Okay, all Miller planes, all these Miller planes are perpendicular to incident X-ray beam. Because These planes H and K can have different values, but its L index is 0. L index is 0 means that plane is parallel to C axis, and here as we can see the C axis is perpendicular to the incident beam. So to show this diffracted X-ray beam nicely, I will draw a separate cylinder over here. Okay, this is the cylinder. And in this cylinder, I will show diffracted X-ray beams. Now the planes. Here in this case, let me show the horizontal plane. This is the horizontal plane. Here is the incident X-ray, and this is the crystal over here. This is the crystal. Now the planes which are parallel, the planes which are parallel to C-axis and perpendicular to the incident beam, they diffract in the horizontal plane. There are several planes which are rotated. Particular plane satisfies the Bragg's law. Rotation theta, that theta angle satisfies the Bragg's law, and we get diffraction in the horizontal plane. So this is the horizontal plane. So all those planes which are parallel to the C axis, they are diffracted in this plane. So for this plane, L index is 0. Then we will consider inclined plane. Consider inclined plane to rotation axis, like HK1 and HK bar 1. This is bar 1. So these are the two set of planes. HK1, H and K can have any values, and other one is HK bar, 1 bar. So these planes are, if this is the rotation axis, this is here rotation axis, and these planes make some angle with respect to rotation axis. I am showing only one plane here. There are many planes. So this is the plane, and Miller indices of this plane is HK1, and this plane makes an angle a phi with respect to rotation axis. Then such planes diffract in the plane above the horizontal plane. like this. So all those planes who are having Miller indices HK1, they will diffract in the plane above this horizontal plane. So here what we get is this is the plane which is above the horizontal plane, and we get diffraction from the crystal like this. I am only showing the few diffractions. And for this plane, the value of L is equals to 1. As I shown here, those planes who are having Miller indices HK1 are inclined to the rotation axis, makes an angle phi with respect to rotation axis. Such a plane diffract in upper plane. Then another planes HK bar 1, this is the rotation axis again, and HK bar 1 planes are inclined in this direction, and we get X-ray diffraction in the plane which is lower side of horizontal plane. So you will get the reflections like this, and Miller indices of this plane is HK bar 1. HK bar 1, and these planes diffract in the lower plane. This is the lower plane, and here we will get the diffraction diffracted X-rays. So inclined planes to the rotation axis diffract in upper and lower plane with respect to horizontal plane. And for this, L equals to -1. Similarly, you will get for HK2 and HK2 bar. Similar X-ray diffraction for HK2 and HK2 bar. So for HK2 bar, we will get the diffraction in this plane. So for this, L equals to -2, and here L equals to 2. So diffraction would be here. showing only few diffracted planes, diffracted X-rays. So like this, you get different planes. Then we can take out the film, X-ray film, and develop and fix it. After we develop that film, X-ray film, and fix it, we will get the film like this. In this film, there is a central layer line. This is called central layer line for L equals to 0. This one is central layer line. And then there is a first layer line in upper and lower plane. This is for L equals to 1. This is for L equals to minus 1. We can say this is the first layer line. Similarly, you get the second layer line. Here L equals to 2 and here also L equals to minus 2. So these are the second layer lines, and on these layer lines you will see diffracted spots like this. And from this film you can find the distance between the central layer line and the first layer line. It is observed that what is observed? It is observed that these layer lines are depending on separation of lattice point on C. This layer line separation depends on lattice point on the C-axis. Let me show you this. Suppose these are the two lattice points on the C-axis. This is incident X-ray beam, and at that point the diffraction takes place. This is a diffracted rays. Now here you can easily say that the distance between these 2 points is equals to C. And as I said, the C axis is parallel to the rotation axis. And to find the path difference, I have to draw the normal on this ray. This is the normal. And this angle is phi. Then the path difference is C sine phi. So from this equation, C sine phi equals to n lambda, we can find the C. For first layer line, n equals to 1. And so this equation is C sine phi is equals to lambda. And here sine phi, we can find the sine phi. And sine phi is nothing but distance between first and central line. Central layer line and first layer line. divided by radius of cylinder. So from this diagram, we can find this distance between central layer line and the first layer line. You need to take average of these two. This is also distance between the central layer line and the first layer line in below plane. And sine phi is the distance between these layer lines divided by radius of the cylinder. You can find sine phi. Then lambda is known. Then you get the value of C. You can find the C. So by this equations, you get the lattice constant C. Similarly, we can find A and B. To find A and B, suppose if you want to find A, then you have to mount crystal with A axis parallel to rotation axis. Then you will get the value of A. Similarly, you can find the value of B. For that, we have to mount crystal with B axis parallel to rotation axis, and you will get the value of B. So by this method, you can find lattice constants A, B, and C, and you will get the dimension of the unit cell.